Solving problems in rotational dynamics, first thing, always draw a diagram. Make sure you draw the radiuses, make sure you draw masses, and so on and so forth. Decide what's important in the system, and also choose a coordinate system that makes sense to you. If it makes sense for some reason to choose an XY coordinate system, go ahead and do that. If it makes sense to choose a R theta coordinate system, then go ahead and do that. Choose the point that you know that it's going to be rotating about. Draw a free body diagram for each object, include all the forces that are acting on it, and now their radiuses. Find the axis of rotation, calculate all the torques of a body, and then we're going to write Newton's second law. Sum of all of those torques that we've calculated is going to be equal to the rotational mass multiplied by the angular acceleration. You've gone ahead and you've calculated out what all those guys are. Now let's see if we can figure out the rotational inertia. It might tell you that you have a disk or that you have a rod. You might need to go look that up, or you might need to add it together as I did on the last slide. And then we're going to apply Newton's second law. More likely than not, we're going to solve for the angular acceleration. Then we can go back and start to put those into our rotational dynamics equations and solve for velocities if we know time, so on and so forth. Lastly, just make sure you check your answer, make sure it makes sense. If something is spinning at 5 bazillion radians per second, that might not necessarily be right, especially if you're talking about like a merry-go-round or something like that. So we've covered some basic definitions, some dynamics, and Newton's second law, so now we need to talk about rotational kinetic energy. We can write the kinetic energy as the sum of 1/2 mass velocity squared. These are the linear definition, and then go ahead and start converting these into rotational quantities, knowing the relationships between them. It turns out that we can write an object's rotational kinetic energy to be related to 1/2 multiplied by the rotational mass right there, and the rotational velocity omega squared right there. So if we know an object's rotational mass, if we know how fast it is rotating, we can go ahead and calculate very simply its rotational kinetic energy. An object can have both translational and rotational motion, therefore it can also have both translational and rotational kinetic energy. We could write its kinetic energy as 1/2 mv squared multiplied by 1/2 I omega squared, and since the object is rotating, we know that it's going to be rotating about its center of mass, so the velocity is going to be about the center of mass. That's where it's going to rotate about, and similarly the rotational, the I is also going to be about the center of mass, because that's where all the motion happens relative to. If we look at the conservation of energy, we know that if we have several objects that are put on the very tippy top of a ramp of height h, they're all going to have the same gravitational potential energy, which is going to be equal to the mass times the gravity times the height. However, if we let an object roll down the incline, rolling without slipping, it's going to have its translational kinetic energy, 1/2 mv squared, in addition to some rotational kinetic energy, 1/2 I omega squared. What that means is the sum of the energy that would normally go to the velocity is now going to go to spinning this object up because it has some rotational mass. The larger that rotational mass is, the less energy that's going to go to an object's velocity. So if I had a hoop, an empty can, a solid cylinder, and a sphere, and a box sliding down the hill, a box is going to make it down the fastest, assuming no friction, because none of the energy has gone into rotating that box. Something like a hoop is going to have all of its mass located on the outside of it, making the rotational inertia the largest compared to, say, open can, solid cylinders, or sphere. So a lot of the energy is going to go into rotating this hoop up, and not a lot's going to go into the velocity. Of course, energy is going to be related to work. So for example, we know wind energy works. What is going on here is we're going to have forces that are applied at some distance away from a point of rotation of the windmill, and it's going to trace out some change in position over some change in time. If we think back to our definition of work being equal to the force multiplied by the distance, then simply taking everything we know about forces, torques, distances, and the relationships between angular and linear, we can go ahead and come up with the work is going to be equal to the torque that was applied, as well as how long it was applied for. The angle will, of course, be in radians, and very similar to the translational amount of work, the units is still going to be in joules. So we've talked about energy and work, much like with the linear sense. Next thing we're going to talk about is going to be angular momentum. We used to write that our momentum was equal to our mass times our velocity for the linear sense. For the angular momentum, it's going to be equal to the rotational mass multiplied by the rotational velocity. Looks very similar now. We can also write our torque to be related to the change in angular momentum divided by a change in time. Much like we had the impulse relationship for the forces, it is still the same here. Lastly, if the net torque on an object is 0, then the total angular momentum is going to be a constant. It's not going to change. Much like if we had no forces on an object, then the momentum of the system was going to be a constant. So with no net torque, then we can say that this quantity I times omega is never going to change. It's always going to be what it was initially, which is going to be equal to a constant. We can see this conservation in systems that have no torques acting on them. For example, in the case of a figure skater, we know that her angular momentum beforehand can be written as I naught omega naught. If there are no net torques acting on her, this frictionless ice, then if she were to bring her arms in closer to her, essentially changing her rotational mass, we know that bringing the arms in is going to bring the mass in closer to the axis of rotation, that this quantity, I multiplied by omega, must be the same as it was initially. Her angular momentum must be a constant. Since I has gone from being a large quantity to a smaller quantity, her angular velocity must go from being a small quantity to a large quantity through the conservation of angular momentum. The same type of thing for a diver right here, where the diver jumps off the board. Her angular momentum right here must be equal to her angular momentum right here, must be equal to her angular momentum right here. And so here has the smallest rotational mass, therefore she has the largest rate of change of her angular position, her largest angular velocity. Lastly, just some thoughts on the vector nature of these angular quantities. I in the book have both been drawing vector symbols on those, but I haven't told you which direction they point. It is not logical to choose our vectors in this xy plane right here, because they will always be changing direction. The only way to define something with, I'm going to use angular velocity right here as an example, but it also applies to angular acceleration and so on and so forth. The only way to have a constant angular velocity vector is to choose its direction along the axis of rotation. So in order to find that, we have to do what's called the right-hand rule. So if we consider this disk that is rotating right here, what we're going to do is we're going to take our fingers and make our fingers point in the direction of rotation. We're going to curl our fingers around the axis of rotation, and in this case we're going to be making a thumbs up symbol. The direction of our thumb is also going to be the direction of the angular velocity. I said earlier about torques that we typically define counterclockwise to be positive and clockwise to be negative. That is also true of angular velocity, acceleration, and so on and so forth. So if this disk was rotating in the opposite direction, then I would have to curl my fingers around such that my thumb would point downwards along the axis of rotation, and I would have my angular velocity pointing in the downwards direction. As I said earlier, angular acceleration and momentum also point along the axis of rotation, and simply recalling that the angular momentum is going to be the rotational mass, which doesn't have direction, multiplied by the velocity, we can use the same right-hand rule to look at this person right here that is going around with a constant angular velocity. I'm going to wrap my fingers in the direction of his motion, so kind of in that direction right there, curl my fingers around the axis, and my thumb is going to point up. If I look at the disk, he's kind of going on a treadmill disk right here. I'm going to here point my fingers along the direction of rotation, and the only way that I can curl them around the axis is if my hand is pointing in the downwards direction. Apologize, I'm no artist. So in this case, the rotational velocity and the rotational momentum of the platform is going to be in the downward direction, while they're in the upwards direction for the person who's walking in the opposite direction. Lastly, just the summary slides for the chapter. I'll page through these real quick.